Okay, so what we're going to do is we're going to look at the math of particles in an ideal gas. And we're going to do it as quickly as we can. Good, it's working. So it turns out that if you think about a gas, we've talked about this before, but there's an average kinetic energy for particles inside there, but they're not all moving at the same velocity. So this is a box filled with gas. They're not all moving at the same velocity. They have a distribution of energies. Oops, I wish I could draw a straight line. A distribution of energies, and I believe it's often called the Boltzmann curve. At least I always call it that. I think it is. And what it talks about is if this is the number of particles along the x-axis, number of particles, and this is the kinetic energy of the particles, the absolute kinetic energy of the particles. So we're thinking about the particles in here. If we were able to show this, you would get a distribution that looks something like that. Okay? This being the average or the mean, okay, of these particle energies. Okay? And this is what we are detecting as temperature. It's a direct measure of this mean value. Okay? If we heat up the chamber, okay, if we add heat to the chamber, this distribution changes a little bit. Okay? As it gets warmer, I'll use an orange color to indicate warmer, there's still the same number of particles, but their distribution changes. So now we get an average EK that's somewhere over here. But what this means is, okay, there are some particles with very high energies, right? And there's some particles with very low energies. So if you say take this same distribution, but now you talk about a solid, there may still be some particles in there with enough energy to actually be in the gas phase, and they can leave. Ah, you are right. My bad. I rushed that. Sorry. Let's fix that. That's a great call. My fault. This is energy here. Sorry. This is number of particles here. My mistake. I hope that didn't screw you up too much, okay? My brain was talking correctly, but I didn't write my axes correctly. Sorry. That's what we mean, okay? Now, what if I were to exchange the particles in here at the same temperature for much heavier particles? Like, say we were originally with heliums, now we're with nitrogens, okay? Well, the kinetic energy is the same, right? The EK is the same, so the curve isn't going to change. But what can we think about the velocities of the nitrogens with respect to the velocities of the, say, heliums or lighter particles? Slower, must be slower, right? And that comes from our understanding from before that the kinetic energy is half mv squared. So as the mass goes up, the velocity would go down for the same given kinetic energy, okay? Now, it turns out that there's an equation that talks about this, and that equation is this. It's EK bar. What does the bar on top mean again? Average EK is equal to 3/2. This has to do with the degrees of freedom that the particles are able to move in a gas. Half, not sure, something to do with the average. Then there's a constant, and it's called the Boltzmann constant. No, it's a number. It's a number. And T being Kelvin temperature. So what this is saying is you can find the EK, or the average EK of a particle, just simply based on the Boltzmann constant and the Kelvin temperature. And then, if you also know the mass of the particle, you can make it equivalent to your other formula for kinetic energy. So what you can do then is, if you know the Kelvin temperature, using the Boltzmann constant and 3/2 of that times the Kelvin temperature, you can actually figure out what the average EK of a particle is, and therefore, if you know its mass, what its average velocity would be. Okay? I can't derive this for you, unfortunately, but I can tell you what the Boltzmann constant is, and you can tell me what units it will be in by looking at that. So it's 1.3806. Do you think it's a small number or a big number? It will be small. Okay. What units would it have to be in? What's that? Joules per Kelvin, or in its complete SI units if you want. Meters squared, kilograms per second squared per Kelvin. So kilogram meters squared per second squared is the joule, right? Force times distance. So there it is. There's the Boltzmann constant. So should we really quickly do an example here? Find the average velocity of a helium atom at 100 degrees C, 0 degrees C, and negative 273.15 degrees C. This only works if you're dealing in kelvins. So we need the Kelvin values for these. So here's 0K. I think you can already figure out what the velocity would be there because a 0 in your formula anywhere when you're multiplying gives out a 0. 273.15K and 373.15K. Okay, so these are the values that go in there. So the first thing I'll do in the first case is let's just find that EK. What temperature will we do? Okay, let's do 100 degrees first, just for example. And EK is 3/2 Boltzmann constant times T. So in this case, it should be 3/2 of Boltzmann constant. Some calculators have the Boltzmann constant actually built into them, so that makes it quite a bit faster. And 373.15K. So you're canceling out, and you should get 7.727 times 10 to the negative 21 joules. So what does that number represent then? The average kinetic energy of a single particle of helium, okay, if this is helium, of really a single particle of any gas at that temperature.
Just a few announcements before
and then
are dismissed. Messages in the office for Harley Booth, Liam Duchesne, Ty
we
Forkey,
want this.
Peter Fenton, and Ricky Kaminsky. Students and staff wishing to march in the Pride Parade on Sunday, June 14th are asked to attend a very brief meeting today at lunch in the art room. Cafeteria today is serving pies, apple, lemon meringue, banana cream, and chocolate. There's open gym basketball today at lunch, and the grad band is canceled at lunch today. Those are all your announcements. Thank you.
Okay, there's the
glasses was turned in. Please come to the office to identify them if they are yours. Thank you.
Okay, so there we go. A helium particle. This is the mass of the helium particle right here. Okay, there's the kinetic energy we figured out. There's your formula rearranged. Should be 1.5 times 10 to the 3 meters per second. Yeah, it's pretty fast. It's pretty fast. Okay. That was at 100 degrees or 373K. Now what you can do, since both of these are equivalent to each other, you guys can do this on your own. What you can do is you can say, let's make these two equations equal to each other, right? If we want to solve for V, the first thing we would do is multiply both sides by 2. So 2 times 1/2 is just cancel off. And 2 times 3/2 should be 3. So what we should get is velocity of a particle is equal to 3 times the Boltzmann constant times the Kelvin temperature divided by the mass of a particle of that substance. Okay? So you can pretty quickly, if you're asked a question on this, work out that this is the way to, and this is a square root, by the way, just in case you didn't notice, figure out the velocity of these objects at different temperatures. When we drop to 0 Kelvin, right, put a 0 in here, and you end up with a 0 velocity. Okay, does that make sense? The biggest trip up people will make when they're asked questions on this is they'll be given a value in Celsius and they'll forget to do it into Kelvin. It does not work in Celsius, okay? And we can talk about why that is later, or you probably intuitively already know why that is, okay? All right, thank you very much.